Okay, so in the last class we had been looking at Huffman coding, and I'm very keen for you to get to grips with that because it could be an exam question or half an exam question, but once you know it, it's free money. It's very easy. And with Huffman coding, you assigned short codes to the frequently occurring symbols and longer codes to the less frequently occurring ones. And then although it was kind of swings and roundabouts in terms of the length, because you won more often than you lost, overall then you save a lot of bits. What we're going to look at today now is an algorithm which takes it a step further. Okay? So if I said to you, okay, I want you to transmit a message. So let's say we're back in our sort of semaphore scenario, and I'm asking you to transmit a message from A to B. And I'm saying, with this Huffman coding we can save lots of space. And you're sending it bit by bit. If I was to say to you, okay, so send the letter T. You're like, well, hang on a minute, no, we don't have our table yet. I want you to tell me the message, the whole message in its entirety, and then I'll work out the frequencies, and then I'll work out the variable length codes using the algorithm, and I'll get my tree, and then I can start the message. And you're like, okay, but I don't know what I'm going to say yet. Well, then Huffman doesn't work. So for Huffman coding, you need to know the entire contents of the message in advance. So if you have a book and you want to compress the book, well, you have the book there, you have all the text in it, so you know what to do. Okay, so that's a problem. Also, you must transmit the dictionary then as part of the message. So before you start, you must say, okay, listen guys, now this is the dictionary that we're going to use. So there's a bit of overhead there. Now, in fairness, in the grand scheme of things, the overhead isn't huge, but it is an issue. Okay. Now, here's another thing to consider. We know, for example, that in English, like E and T and A and O and N, those are fairly frequently occurring letters. But we also know, for example, that TH as a pair of letters, that occurs quite a lot in English, doesn't it? I mean, even THE is probably up there with some of the most frequently occurring, or even THE space, if you think about it. It's probably way up there with the most frequently occurring symbols. I'd imagine in most documents THE space occurs more frequently than Q. So what if we were to have a scheme where you didn't just have a variable length code for a frequently occurring character, but you gave a variable length code to a frequently occurring sequence of characters? That could be pretty powerful too. So you might decide that 1001, that by itself means THE space. You could probably do a lot of damage with that, that's pretty impressive. So the scheme we're going to look at today does all of those things. It sets out to code sequences of characters if they occur more than once. And it also does it in such a way that the receiver builds up the table along with the transmitter. So you don't need to send it all in advance. Okay? So this is what I was saying there. We know, for example, that E and ETA, O, and N stuff would be fairly frequently occurring characters on their own. But we also know that sequences of characters might also be very popular. And so we could give those their own codes in a table. And so Lempel and Ziv devised an algorithm, and then it was improved upon by Welch, and we got Lempel, Ziv, Welch, or LZW. And this is useful because the transmitter and the receiver build the tables as they go. So the receiver, when it gets a new symbol, you know, it adds it to the table, but it knows what the transmitter is doing, so it builds it up as it goes along. So you don't need to actually send the table. Okay? And then sequences of characters have entries in the tables as well. Now, so the idea is that both the transmitter and the receiver start with the same fixed length single character dictionary, probably the ASCII table. I mean, in reality, some of the characters at the bottom, you know, some of the space at the bottom of the ASCII table which isn't used really, they might dispense with or use that for something else. Or they might decide, no, look, for convenience, we'll just start with the ASCII table, you know, it's no great loss. Okay? Then characters are gathered into a sequence until the next character would make a sequence for which there's no code yet. So basically, when you come across a sequence of characters you haven't seen before, you transmit the code for the sequence without the new character, and then you transmit the new character, and that'll go into the next slot on the table. So if I had T and H in the table already, and then I encountered a T and a H, okay, and then I come across an E, well, then what I do is I send the TH, and then I send the E, then I put THE into my table here, and the receiver at the other end knows, okay, that's new as well, so I'm going to put the TH and E into the table as well, in the next available slot. So at the end, then they end up with the same table. Yeah. So this is obviously a ridiculously contrived example, but let's suppose that, well, for a fact, my favorite restaurant is Wagamama, and let's suppose I move to Australia, and I move to the Australian city of Wagga Wagga, which is a real city in Australia, and I want to tell someone I was going to meet them at the Wagga Wagga Wagamama. Okay, ridiculously contrived example, but you can be pretty sure here we're going to see sequences of characters repeated. Interestingly, in Japanese, that's going to happen anyway. That's a conversation for another time. Okay, so W is in the dictionary. So at the start of this dictionary, we already have the ASCII table. So I'm just showing you the tail end of it there. So up to 127, so we're talking about 7-bit ASCII. So that's our starting point. So rather than fill the slide with that, we just assume that's there, okay? We recognize an ASCII character when we see it. Now, so W is in the dictionary. So we keep going until an unknown sequence is encountered. So WA is not in the dictionary. So so the code for W is sent, okay? And then WA will be added to the dictionary. No, so basically what happens is we send W, we send 87, and then we'll also send in lowercase a, which would be 97. And then we're adding W and A to the dictionary. Okay? So at the receiving end then, goes into the next slot there, which is 128. At the receiving end, the receiver will know, okay, WA is a sequence you haven't seen before. That's going in at slot 128. Okay? Well, actually, did I tell you that wrong? I think I told you that wrong there now. So AG is not in the dictionary. Okay? So the code for A is sent, which is 97, and AG is added to the table. GG is not in the dictionary, so the code for G is sent, and we add GG to our dictionary, to our table. We call it a dictionary. GA is not in the dictionary, so we send the code for G. Now you notice there, as we step through them, like just because we've done AG, doesn't mean that GG doesn't get done then. You know, that G there is being counted twice. Do you know what I mean? It's being represented twice in the table. Each slice, as it's sliding across, is getting done. So GA is not in the dictionary, so the code for G is sent and GA is added to the dictionary. Then we have A space, that's not in the dictionary. So the code for A is sent, and then A space is added to the dictionary. So all we're sending, you'll notice that by the time we're done then, the code for each character has only been sent once. So we've sent W, we've sent A, we've sent G, we've sent G, and we've sent A. So we haven't done anything we wouldn't have expected really so far. We're building up the table as we go, and then at the receiving end, the receiver has the cop on to also build up the same dictionary, same table. Now, space W isn't in the dictionary, so we send the code for space, which is 32, and we add space W to the dictionary. No, WA is in the dictionary. It's there at slot 128. So we keep going, we have nothing to do yet. WAG isn't in the dictionary. So we send the code for WA, which in this case, in our dictionary here, is 128. And then WAG is added to the dictionary. Okay. GG is in the dictionary, so we keep going. GGA is not in the dictionary, so we send the code for GG, which is 130. And we add GGA to the dictionary. A space is in the dictionary. It's there at slot 132. So we keep going. A space W is not in the dictionary. So we'll send the code for A space, which is 132. And then we'll add A space uppercase W to the dictionary. W is in there already. WA is in there already. WAG is in there already. That's at what, 135? But WAGA is not there. So we'll send the code for WAG, which is 135, and add WAGA to the dictionary. Now if you think about it from the receiver's point of view, so it knows now that it's done WAG, it's not sure what's coming next. But the next thing out of our mouths is going to be A, or something starting with A. So it'll know later when it arrives. And then the important point is that it's building up the table as we go. I think the job of the receiver is actually harder than that of the transmitter. So WAGA is added to the dictionary there. A is in the dictionary, so nothing to say there. But AM isn't in the dictionary, so we send the code for A. Can only be A anyway. We're only going to send something that started with A. There was nothing that it was either going to be A or AG, for example, but it had to start with A. So we're going to add AM to the dictionary. M is in the dictionary. MA is not in the dictionary at this stage. So we send the code for M, which is 109, and then we'll add MA to the dictionary. Okay. A is in the dictionary, of course. AM is in the dictionary. It's there from just a second ago. 137. AMA isn't in the dictionary, so we'll send the code for AM, which is 138, and add AMA to the dictionary. And then we send it. It's at the end. So we might need that kind of an end of file, end of message marker as well, or something. But anyway, so we'll send the code for A, which is 97. Okay. And so then we're done. Anybody see any of that again? So it's the important point really is that the transmitter and the receiver are building up the table as they go. Now there are fairly complex variations on this then, because you might decide that you've only got 256 slots, or you might decide you've only got 1024 slots. And so then you have to do things like keep track of how often something is used. If a combination, you know, if GAM hasn't been used for the past 1,000 symbols or something, you might decide, okay, I'm going to drop that from the table. You know, so as the message grows and as the message is transmitted, the table might shrink and grow, and things will be dropped and things will be added. You can have all these various complicated variations. And the key there is that the transmitter and the receiver know the scheme, and they'll always keep track of they'll always keep the same table going. Okay, so there are variations. But in our simple version here, you just keep going. You just keep adding to the table. Any questions on any of that? Okay. So, in this example then, the receiver received 87, which was the uppercase W, wasn't it? 97 was lowercase a. 103 was the G. 103 was the G. 97 was lowercase a. 32 we know is space. No, this 128 then is not an ASCII value. That was one of the things that was added to the table. The first thing that was added to the table was the WA. So 128 was WA, and so it goes on like that. So as this progresses, the receiver has built up the table also, and so it knows what the transmitter is talking about then when it sends a code for a sequence of characters. So at the receiving end, what happens is you take the string that was just output with the first letter from the next decoded value, you put the two of those together and you add them to the table. So that's how the receiver does its business, and make sure that it always has a copy of the current table. Now, you do need some sort of end of file marker. And of course, the size in the dictionary, you know, really needs to be finite. And so there are various tricks you can use then. You can prune the table. So at both the transmitting and the receiving end, there might be a counter as to how often something is used, or there might be a counter something as how recently the sequence has been used. And if it hasn't been used in a while, or isn't looking very popular, it gets booted out of the table. So if it comes back, you'd have the expense of putting it back into the table again. But if it's never seen again, it was only taken up space that could have been used by something else. So in a novel, for example, a character might appear in the first 2 or 3 chapters and then get killed off. And so that name is never used again. So you could get rid of it. Might happen, he miraculously comes back. He was only lost at sea, and actually in the last chapter, you know, he arrives again. You know, big deal. Just slot him back in. So it allows the table to, for the most part, be adapted to the content as it is at the moment. And the cool thing about this is that you get to use not only single characters, but you have sequences for reoccurring combinations of characters, which we know are very common in most languages. Okay, any questions on any of that? Okay, so here then is an exercise for you. So this is a person. We're going to play charades, whatever. This is a person. What is, what's the name? So your starting point would be the ASCII table that I gave you there. So just assume it's a bog standard ASCII table. Okay, up to 127. So who is this? And no cheating.